Okay, well, everybody, welcome. Hello, thank you for joining us today. My name is John Quigley. I'm the Assistant Dean for Advancement in the College of Arts and Sciences at SU, and I want to welcome you to today's Arts and Sciences Alumni Academy. College of Arts and Sciences periodically offers these faculty Zoom talks as a way of letting alumni know about the great research and scholarship happening in the college. Today, we are pleased to present the Ozempic Challenge, the ups and downs of obesity drug development, with Professor Robert Doyle. Before we begin, I have a few announcements. First, I want to ask everyone to make sure their microphones are muted. This will ensure that everyone can hear our presenter clearly. I want to let you know that we're recording this event and it will be shared on the college's website and YouTube page for people to view after this evening's presentation. Closed captioning services are provided for this event. And you can direct your attention to the chat for additional instructions on the closed captions and a few other informational items. Lastly, I want to remind everyone that today is Giving Day at SU. You may have gotten some emails and announcements about it. On Giving Day, once a year, we ask alumni, parents, and friends of the university to make a gift to support an area of the university that is important to them. If you've already made a gift for Giving Day, I want to thank you. And if you haven't, I want to ask you to consider making a gift. We're going to put a couple links in the chat, which will take you to the giving pages. The first link is to make a gift to the College of Arts and Sciences, where you can support either the Dean's Fund, the Scholarship Fund, or the Student Experience Fund. And then the second link is going to be for the Department of Chemistry. Today's speaker is a professor of chemistry, and you can support him and the other amazing faculty and students in the chemistry department with a gift to the chemistry department. So thank you. Right now, I want to introduce our speaker for the evening. Professor Robert Doyle is the Jack and Laura H. Milton Professor and Dean's Professor of Chemistry. He is a medicinal chemist with an interest in pharmaceutical drug development for the treatment of obesity and type 2 diabetes. Professor Doyle received his PhD in chemistry from the University of Dublin and completed a postdoctoral research fellowships at the Australian National University and Yale University prior to joining the faculty at Syracuse in 2005. I know we're all excited to hear from Professor Doyle, so Rob, I'm going to turn it over to you.
Thank you. Okay, let me see here. I'll make sure this is working. Continue to share. Please let me know if that is not visible to everybody. I will speak slowly and clearly so my Irish accent doesn't throw you off along with the science. So feel free to ask questions as we go, or of course we can answer questions at the end. So my research is very much in the pharmacology space. So we are in the drug development business, in the drug development space. And here at SU, in my lab, we are very much interested in endocrine disorders. Big picture, they would include diabetes. They would include obesity, so excess weight. And also, they would also include, people are still trying to be admitted, John, so I think keeps popping on my screen. I don't know if you can fix that.
We should have them all, Rob, at this point.
Okay, it just keeps popping up on my screen.
Yeah, we'll take care of them as they go.
Okay, so everybody can see it. All right. So we are very much interested in this sort of space. So I will like to thank the people who do all the work. So obviously, as the professor, I don't actually do anything. In the lab, the wonderful students here at SU, the grad students whose names are in navy blue there. And then the undergraduates, of which we currently have 9 in the Doyle group, ranging from freshmen to seniors, have all, done really a yeoman's service. And I thank them all. And you'll see a lot of what they've been up to as we progress through today's talk. Also, I cannot do this without funding, and this is funded extensively by the National Institutes of Health, also by the Department of Defense. And most recently, I started a company with investors and with the support of Syracuse University, who now co-own a little piece of this company. And that is called Coronation Bio. And we have 2 compounds moving towards phase 1 clinical trials, hopefully in mid-2026. So, about 15 months or so from now. which we'll be very excited about.
Rob, I'm sorry to interrupt. You need to share your screen again, I think. We're not seeing the slides.
No, weird. Okay. Let me go back again. So round 2, does that work?
That's good. Thank you.
Okay, so oh yeah, they'll continue to share. Okay, Zoom teething problems, isn't it always? So basically, these are the people who fund all the work: the National Institute of Health, the Department of Defense, and a lot of the work is preclinical, so it has to go into animals before we can really make it safe for use in humans, of course. So a lot of the preclinical work is done with my collaborators at Seattle Children's Hospital. This is Christian Roth, Matt Hayes' group at University of Pennsylvania, Bart de Jong's lab also at the University of Pennsylvania in the psychiatry departments, and Amber Aladef, who is at Monell, which is also in Philadelphia. And Amber is an expert on nausea, conditioned taste aversion. So signs of malaise as it pertains to the brain's reaction to drugs and response to various different environmental stimuli. If you didn't see it before, you can see it here. This is the students again that you didn't get to see the last time. They're the ones who do all the work. We've got currently 7 graduate students, and I have 9 undergraduates ranging from freshman to senior year. And they are pretty fantastic group. Very lucky to have them. Okay, right. So let's get down to brass tacks with all the thank yous out of the way. What is the problem? Why do we care? Well, I think we'd all agree obesity has become a major problem. We have an epidemic of overweight and obesity. And the latest estimates, and this is courtesy of the latest figures put together in this report in 2024, says that in 10 years, over 50% of the world, not just the United States, 50% of the world will be overweight or obese. So this is a problem that is growing and growing, at a rapid and quite scary rate. Okay, so if we want to get more specific to the United States, we are certainly a contributor to that problem. You can see both men, women, boys, and girls are all trending upwards in the percentage of obesity. And by 2035, you can see the US is estimated to have 60% of its men, for example, projected to be obese. Okay, so it is a huge problem now and will only get worse before it gets better if we don't do something about it. Okay. So what is the problem? If we get down to the more granular level, it's actually all about energy, right? And so for us, in very simple terms as humans, energy and the seeking of energy comes from the brain. So it is under brain control. Go find food, consume food, go get more food, consume more food. It's an neuroendocrine process. And so energy balance is basically all about the brain. And so everything we do in the Doyle group is about modifying the neuroendocrine pathways, so the hormonal pathways and the neurotransmission pathways in the brain as they pertain to various different ailments. As I said, diabetes, appetite regulation, etc. The problem is there are multiple signals in your brain, multiple targets in your brain, and really multiple regions of the brain that control appetite and satiation, the feeling of fullness, or they control how your stomach empties. And all of those things feed back into this concept of, are you full? Are you not? Should you eat more? Should you not? And they're all redundant to each other. They're all backing each other up. So even if you block one, there are other systems that will supersede those, and you'll go out and consume more. So the very simple idea of saying, okay, if I asked you to spend the next 3 days eating nothing, you would find that incredibly hard to do. If I asked you to spend the next 3 days eating as much as you wanted, you would have no problem doing it. And that's because, of course, evolutionarily speaking, we usually, as a species, had a lack of food. And outside of humans, the history of life on this planet is a history of living close to starvation. So all animals on this planet, are always looking for that next meal and are always that 1 day or 2 away from starvation, right? Obviously, now we have a superabundance of food, but we've evolved to take every feeding opportunity we can get because our survival may depend on it. So we are essentially in full eat mode all the time. And that is, of course, a very sensible way to be as you evolve in a situation where food is very scarce, very hard to come by, and might be the last meal you get to consume for several days. So you must take it when you have the opportunity. So essentially we're primed that way, right? And of course, what better food to eat than high calorie foods, right? If you're going to eat high calorie foods. That's where energy comes from. And so we've evolved a sweet tooth, right? We know that certain foods are going to be really rewarding in caloric intake. And so if you do a good job and find something really sweet to eat and give your body lots of sugar, your body will respond to that sugar by making you feel great, release dopamine and endorphins. And again, that tells you go back and find more of that. More chocolate, right? And so we are essentially, as this book says, born to eat, right? Okay. So in other words, we're in a constant on state, but it's more than that. And it follows on from that. The human obesity is not just driven by this metabolic need alone then, right? The reward systems of the brain are giving you credit for eating high calorie foods. And you are becoming essentially wired to go back to them again and again and again because your brain says they're good for you, get them into you because, you never know where your next meal is coming from. Now, of course, not a problem. This is 2025 in the United States. You can walk to any restaurant, any, corner market and get yourself something to eat, right? It's not like we're back on the prairies 10,000 years ago looking for our next meal. Unfortunately, we haven't evolved past that yet. So essentially, we have a problem. Now, this is a little bit complicated, but if you bear with me a little bit, you can see in the negative on the left side of the curve here, you can see, let me see, can I use this little arrow here? Let me see, maybe not. If you can see on the -2 on the axis there, you'll see once you drop down below this this fullness line, you go into, if you're below the fullness line, you're hungry. So you'll start to eat. And we call that ingestion, of course. Up goes the amount of food and you move into a fullness space. We all know as soon as you get a feeling of fullness, you typically say, I'm done and I'll stop eating. That's satiation. That's the, okay, I don't feel hungry anymore. Then how long that fullness lasts before you feel hungry again is satiety. And so you have two sort of aspects of your eating behavior. One is I'm hungry, I'm going to eat till I feel full. Now, how long will the fullness last before I eat again? So satiation and satiety. Drugs today, the famous drugs today, Ozempic, Zepbound, Wegovy, the ones you're seeing, absolutely everywhere. They are really pushing this idea of satiety, feeling full. So they're not blocking hunger per se. What they're doing is they're keeping us in the satiety end of the realm. Now, if you eat and eat and eat and eat and keep eating, most of us know what happens. You'll end up feeling sick. You'll end up feeling, oh my God, I've eaten too much. I feel like I'm going to vomit. I feel really nauseous. I got to go lie down. I feel really low energy now. And so that again is your body saying, stop eating. You've had enough to eat. You need to stop eating. And if you keep eating, eventually I'm going to make you feel sick because it's the only way to eventually stop you from continuing to eat. So that is the off switch, but it's the off switch taken to the extreme, right? So what is that off switch? Well, the off switch and the cornerstone of all of these drugs that you see on the market now is GLP-1 or glucagon-like peptide 1. So what you often hear about Ozempic, where you hear about Wegovy and Zepbound, et cetera, is that they're GLP or GLP-1 drugs. And essentially that just means they're based on this little peptide you see down here. You don't worry about the letters, HAE, GT, FT, they're all little amino acids and they make this little peptide. And you make it in your gut. So this is something you make yourself. It's made in your stomach, in your intestines, and it travels across into your bloodstream, and it goes to your pancreas, and it causes insulin to be released, and that helps control your glucose levels. This is why these drugs also work for diabetes. But it also travels to your brain, and it works in your brain to have your brain tell your body, stop eating, right? And if you don't, I'm going to eventually make you feel sick because I'm also going to trigger these vomiting and nausea receptors in your brain. So this is essentially an off switch. It's an off switch that says we have a problem here. We've got too much sugar in our blood. So we're going to solve it by releasing insulin. We've got too much food in our bellies. we're going to, you know, overload. We need to stop. Okay, I'm going to make you feel sick. And that's going to stop you from continuing to eat anymore. I'm also going to stop your stomach muscles from working so you can't empty food out into your intestine and you're going to mechanically feel full. Now, this might sound familiar to anybody who's ever taken Ozempic or has read anything about Ozempic. The side effects are nausea, vomiting, and gastric motility issues, right? And that's because that is the natural response that is supposed to happen when we're driving the appetite off regulation. But of course, because we're giving you high doses of a super active version of GLP-1, we're pushing the system right the way down into that negative domain, if you will. And of course, while that is great for losing weight, it is obviously driving considerable side effects because it was evolved essentially to do exactly what it's doing, right? And so this is an off switch, but it sounds, based on what I'm telling you, it sounds like it's a toxin, right? And actually, it probably evolved from one. So this is actually work that I've done with Professor George Holtz, who's my colleague at SUNY Upstate here in Syracuse. And Black Widow makes a Black Widow GLP-1. So they actually make it, but they use it in their venom. So we actually found a BW, you'll see in this little graph on the bottom right, a Black Widow GLP-1. And it's actually a very potent GLP-1 agonist. So it activates the GLP-1 receptor, including the human GLP-1 receptor. And so indeed, well, we found it in the Black Widow spider. It was originally found, the drug that became the first FDA approved system was actually a toxin found in the saliva of the Gila monster. So if anybody's from Arizona or lives out in the Sonoma Desert way, you've probably seen these. These are native to the Sonoma Desert, including Arizona, and they can give you a nasty bite. They have a toxic saliva, and one of the ingredients in the saliva is a version of the human GLP-1. So, but in this case, it's not using it to control glucose and appetite. It's using it to kill prey. And in fact, its version, its sequence you can see down here, which is called Exendin 4, very similar to the human GLP-1 I've been telling you about that we make. Ours probably evolved from something like this, in fact, and we repurposed it. But this actual sequence from the saliva of this lizard was the first ever GLP-1 drug on the market. Literally, it was the toxin from this lizard. They discovered it in the saliva. They realized it was much more long-acting than the human version, and that if they put it into a little EpiPen, you can see here, you could inject it, and they could use it to treat diabetes initially. And they noticed you also lost weight when you took it. So it's actually born of a toxin or a poison, a venom. So sort of interesting background history. So from our own human GLP-1, we found a lizard venom version that worked better in humans. So Novo Nordisk called it Byetta, and they came on the market. And it sort of set the stage then for all the drugs we know and love now. Well, at least we know. This was a once a day, and it wasn't very good at causing weight loss. It was really good for treating type 2 diabetes. So they began to make more potent and longer acting analogs. Ozempic has become the sort of really famous one, and Wegovy is just a double dose of Ozempic, so they're the same drug. Just one is prescribed for type 2 diabetes, the other is prescribed for weight loss and or type 2 diabetes. And you can see there are new iterations now, Mounjaro, tirzepatide, Zepbound. So I think the two superstars on the market right now, of course, are Ozempic and Zepbound. And they're both once weekly, and they both cause anywhere from 15 to 20 odd % BMI drop in patients who can tolerate them. So the sort of the history of how we got to where we are now, right? And now it's become a social media darling, right? Everybody's sort of jumped on this bandwagon of, this is going to be a cure-all. This is one of the greatest sort of potential reversers of this pandemic that we're undergoing, epidemic of obesity. The Economist Eat, Inject, Repeat, which obviously it isn't quite that simple. But it's also being driven by sheer weight of numbers and the amount of people who require weight loss, and the amount of people who will continue to need weight loss, and those numbers get bigger and bigger and bigger, the market size is north of 50 billion, and that might be lowballing it, right? So as you can tell, the market of this size is generating a lot of pharmaceutical company interest, right? And of course, it's a social media darling, as I said. The Ozempic weight loss challenge. People are following their weight loss on their YouTube videos, et cetera, et cetera, et cetera. So it's become an enormous deal in society. And the downside of people who don't really need the drug, accessing the drug, which has become a real problem, is that the pharmaceutical companies cannot make it to meet demand. And so people who need it for life-saving treatment of their diabetes, for example, would struggle to get it because of the demand from the obesity space, which in many cases is clinically warranted. They need to lose weight for their clinical health. But in a lot of cases, it's being used, of course, for aesthetic reasons. Oh, I want to lose 20 pounds. Well, maybe you don't need a medication to do that. Somebody who weighs 450 pounds and wants to lose 90 to 100 pounds probably does, for all kinds of metabolic health reasons, right? We know that if you lose this weight, it improves your heart, improves your mobility, your quality of life, your glucoregulation, just all sorts of, your wellness scores, everything. So this has become sort of a downside to the social media storm that Ozempic has created, I guess. So where do we come in with all this background? Well, the real dirty little secret of GLP drugs is that for those who've taken them, you probably know this already. And for those of you who know the field, you've probably heard some stories. But the weight loss drugs are really, intolerable. Most people cannot stay on them for any length of time at all. And those that do will eventually start to see no further weight loss, which requires an increase in dose, and they simply cannot tolerate it. Unfortunately, as I've sort of alluded to moving in here, it essentially works like a toxin. It drives down your weight loss via illness behaviors. So if it makes you feel really sick, you won't eat. And of course, if you don't eat, you'll lose weight. And anybody who's had a bad dose of the flu and stuck to their bed for 3 or 4 days knows that you've probably lost a few pounds. But it's not a particularly great way to treat obesity in the long term. And so what we need are drugs that will give us guaranteed weight loss, but without the side effects. And so that is where, we need to be. And this simply proves it. This is the FDA's adverse events reporting system. This is data that's about 6 months old, so it's up to date. It tracks the use of these drugs in Germany, the United States, UK, France, Spain, Italy, and Japan. And as you can see, regardless of country or which drug you're taking, Trulicity, Ozempic, Victoza, Rybelsus, by 90 days, 30% of patients have basically stopped taking it, and they usually have not lost any weight. And that is simply because they just cannot tolerate the drugs. And as you can see, by day 365, you're talking about 70% of patients in some cases are essentially no longer taking the drug. And unfortunately, once you stop taking it, you typically rebound and regain the weight. So we definitely need better drugs. And that is essentially where we've been trying to come in here at SU. And so the drug I'll tell you about today, and the one that we're pretty excited about, is called GEP44. So of course, 44 being SU's classic number. And so what we set out to do is to make something that would have profound long-term weight loss. It would offer glucoregulation for those who needed it. So it would be a drug that could also treat patients who are obese and type 2 diabetic. We would like it to produce no cachexia or muscle mass loss. A lot of these drugs also cause a weakening of muscle over time. And so obviously we would like that not to be the case. And in particular, though, what was going to be our differentiator was from day one, we were going to only move forward with drugs that did not cause low energy, gastrointestinal issues, nausea, vomiting, etc. So that was actually going to be front and center, as opposed to be something that would be ignored and then just tolerated at the back end after approval. So we decided to completely put it front and center of our approach, was essentially patient compliance. And so how do we go about doing this? So my approach is basically one that we call chemical gastric bypass surgery. So it turns out that if you need to lose significant amounts of weight, one of the effective ways to do it is to have gastric bypass surgery. And gastric bypass surgery does something really unique. It actually causes long-term weight loss, sustained long-term weight loss. And so it can't just be the mechanical effect of having the surgery. There must be something else that's changing. And it turns out there's been, what we believe now is there's a rewiring of all of your hormone levels as they pertain to appetite and mobility in your stomach and the feeling of fullness, et cetera, et cetera. And so what we decided to do in the Doyle group was to go in and say, well, what if we could make a single drug that could replicate the effects, the positive effects that happen after gastric bypass, but without ever having to do the gastric bypass, right? So a chemical bariatric surgery, if you will, right? So how are we going to do that? Well, here at SU in the Doyle Lab, we have quite a pharmaceutical level lab setup. We have multiple robots and multiple synthesis systems that allow us to produce really any peptide or protein that we want to be able to make. I'll show you that in a second. So in terms of physically making them, we're pretty unlimited here. It really comes down to our imagination. The problem is nature has made it so that our imaginations just aren't sufficient, unfortunately. So let's say if we just wanted to make insulin from scratch. So we didn't know the final sequence of insulin. We just wanted to make it. We wanted something that would control glucose levels. Well, insulin has 51 amino acids, and there are 20 amino acids naturally, and any one of those could go in any one of those 51 amino acid positions, which means it's 20 to the power of 51 different proteins, which means we would have to make that number of proteins and screen all of them, and in there would be insulin. But we wouldn't know which one of that number of proteins was insulin. And so obviously we simply cannot do that. We have to be way more sensible, right? And so what we do is we use AI and computer guided design, and we also use natural systems. So in the Doyle group, we typically look at toxins and venoms and naturally occurring evidence-based that we see from nature to actually lean into and predict certain sequences might do certain things under certain circumstances. And then we can model that behavior, and we can pull out certain peptides that sort of interest us, that intrigue us, that we think, well, they might do what we need them to do. And so let's go and screen this model by making these peptides, screening them for function, then going back to these models. And you can see on the screen here, we can do all the modeling and the interacting and the talking, right? And we can, see if our model is right or wrong, right? So the proof will actually be in the final testing, but we have to do something up front that is creative, because we simply cannot do it by sheer weight of numbers, right? So this is a busy slide, I get it, but this is just to give you an idea of what we do. We do the design in-house. We can do robotic protein synthesis. So the robot will make us over 1,000 peptides in about 3 days based on the designs we tell it. We can purify it, characterize it. We can measure its binding. We can see, does it work at the target? Does it not work at the target? We can scale up synthesis, so we can make grams of material. And so just to give you an idea, 100 milligrams probably costs $10,000 if we were to buy it. So the fact that we can make hundreds of milligrams in-house gives you an idea that the ability we have here at SU to be able to do this. This is all contained inside the Doyle lab. We can prep, scale, purify, quantify it, measure its activity at the target. Then it goes to our collaborators at various different places for in vivo preclinical screening. We then optimize it for once a week use, typically in the Doyle group, and then we have ourselves a candidate. So obviously that's a lot of work, but that's essentially the sort of picture. And what you see here on the slide is what goes on in the Doyle lab on a sort of a daily basis. So what does it all look like in the end? Well, this is a picture of GEP44, the green squiggly thing, right? And that is a helix. As you can see, the little beautiful twisting green two-piece. It's got what's called a hairpin loop. So again, it looks like a little hairpin. I've no hair to demonstrate, but you get the point. And this particular structure is what makes it very, very, very special. So you can see it side on and looking down on it, and you can clearly see the two helical loops there on the right side. And of course, we made a lot of peptides to get to this one. And it turns out that this exquisitely designed final shape is critical for its function. Any and all changes we've made to try and make it better, make it worse. So therefore, we have really hit the optimum sweet spot in terms of what this drug does, which I'll show you in a minute. And we made a whole bunch of others of different shapes, and you can see them in the bottom right, that didn't work or worked at some of our targets, but not others. And so GEP44 has become sort of our go-ahead darling, right? So we did publish this, how we got to this point. I know this is being sent out, so if you read down here in this Nature article that we published, you can click on this and it will bring up the entire article and you can read the whole background of how we got there, should you want to, rather than me, drowning you in it right now. I think that's fairness to say. Since we've reported it, Phoenix Pharmaceuticals have started to sell it, unbeknownst to us. So they just decided that they would take the sequence, make it, and put it on the market, and people can buy it now, 100 micrograms for $415 apparently. So if you want to buy some, apparently you can go right ahead and buy some. I would not use it. It is not clinically approved, and they will hopefully make that clear to you. But it has gotten a lot of attention to the point, as I said, that other companies are now making it. So what is so great about it? Well, let me show you what's so great about it. This is Byetta. If you look at the red graph, focus on the red line going down. Okay, as you see each data point as you go down, that shows you're losing weight. So this is in rats. So as you go to higher doses, 0, 10, 20, 30, 40, 50, 60, more of the drug causes more weight loss. And you can see at 60, the highest dose tested, you're getting to about 50% weight loss, okay? But look at the dashed line going up. As down comes the red, so as down comes the food intake, up goes the sickness. And kaolin is essentially just a nausea measure. So as it goes up, the animals are feeling more and more sick, right? Now, if you look on the right at GEP44, this was our first ever indication that we had cracked what it is we wanted to crack from day, that what our target was. Not only is it a much more potent food intake reducing drug, as you can see here at 60, we're down at 90% food intake reduction, and we have essentially no kaolin. So we have triggered that satiety pathway without triggering that nausea, vomiting, malaise effect. So that was the first indication we had something, I think, very special, and we were very, very, very excited to see that. And so again, I'm comparing here to an actual FDA-approved drug, right? So you can clearly see not only are we a better drug in terms of food intake, we are markedly separate. We've separated this illness behavior to food intake. We've pulled them apart, right? The problem is, and of course most people won't know this, but rats and mice cannot vomit. So we can't measure vomiting. It's a very human characteristic. We all know we can vomit. Dogs can vomit. Certainly a lot of mammals can vomit, but rats and mice cannot. And so what we need is a lab model that is capable of actually vomiting, that has the physiological capability of vomiting. And so this is the shrew, and we use shrews. They're actually like little tree monkeys. So they're much more closely related to primates than they are to rodents, even though they look like a little mouse, I suppose. And they can vomit. And as you can see on the right, if we give in red just five units, let's call it 5 units of X4, that's Byetta, you can see the animals are already vomiting. If we go at 10, so even twice that dose, 10 units, we have no vomiting in the shrew, and we have to go up to 60, right? So in other words, 12 times the Byetta dose before we even see a single animal vomit. And of course, we wouldn't dose anywhere near 60 in a human. We wouldn't need to. 10 was obviously already producing 50% food intake reduction. So that is really extraordinary. We've validated that we don't have nausea and we don't have vomiting. And we can go to much higher doses than you could ever dream of doing with these GLP-1 agonists, right? And again, I remember I mentioned earlier, the drugs tend to start to wear off over time. And so what you would love to do is be able to give a higher dose to continue that weight loss progression. And you can't, because if you go up any higher, they're going to feel even sicker. We could start at 10, go up to 20, go up to 30, go up to 40, go up to 50, go up to 60, and it'll probably be extremely well tolerated. And so you can continue to drive really extraordinary weight loss. And if you can tolerate a really high dose, you could probably lose a lot of weight very quickly if it was a medical necessity to do so. Maybe you need to lose 50 pounds quickly to qualify for life-saving gastric bypass surgery. So there's a huge benefit to being able to just remove the side effects that go beyond patient compliance and patient quality of life, right? There is actually, real medical benefits to it, right? So obviously that's very exciting. We were very exciting, but what we needed to do next was make it so that it would benefit a human in a translational sense, by which I mean the human doesn't want to have to inject this every single day. We would like it so that you could just inject it into subcutaneous tissue, just a little shot from an EpiPen, and then it would work for a whole week, and you would be done for the week, and that's it. No side effects, really nice pronounced weight loss, better metabolic parameters in terms of your cholesterol levels and your blood glucose levels. And so we took an approach. This was run by a graduate student who graduated in 2023, Kylie Chichura. And what Kylie did was she set about making it so that GEP44 would stick to albumin, these little white flecks you see in this image of them with the red blood cells. And by sticking to this protein in your blood, it would circulate around in your blood for 4, 5, 6 days and allow it to keep working and working and working and working, instead of being by itself unstuck to the albumin, whereby your kidneys remove it very quickly and it only lasts for a few hours instead of 120 hours or 140 hours, which we can do by sticking it to the albumin in your blood. So could we do it? The answer, of course, is yes. And we made a lot of different drugs. DG is just a Doyle group code. The nicknames are what we've been talking about today, GEP44. So Kylie Chichura made an analog of GEP44, which was this one I've highlighted in orange. And this one has this big greasy lipid fat-like molecule you see on the bottom right. This is essentially just a big long piece of fat. And what happens is if you put it on to the peptide, you chemically put them together, the greasy part sticks to the albumin, and then the peptide is free to react where you need it to react, but the albumin stops it from leaving your bloodstream, and it just keeps going round and round and round and round and keeps hitting its receptors and hitting its receptors. And of course, we have to get it right, how we put them together, because putting one to the other can kill all of the positive behavior that we're looking for. So we have to get that right. So you make a whole lot of different chemical motifs, and you do a lot of chemistry, and you end up with this wonderful molecule, which we call, as I said, GG3. So of course, does it work? Well, I wouldn't be telling you all about it if it didn't. GG3, which is just super duper long-acting GEP44, made here at SU, conceived here at SU, generates the same insulin level response as tirzepatide, which is the current best drug on the market, Zepbound, even better than Ozempic. So in a chronic study out to nearly 2 months, we can show that it works just as well in a diabetic setting as Zepbound does. So that was the first marker that it was translating very well. It also showed similar triglyceride and cholesterol improvements. So just like Zepbound, tirzepatide, after 2 months of chronic treatment, it was actually as good, if not trending slightly better, at lowering your cholesterol levels, or the cholesterol levels. So if anything, we're at least as good in terms of glucoregulation and at least as good in terms of clearing cholesterol as the current best case drug on the market. But we are much better at producing weight loss. So we are just as good at glucoregulation, just as good, if not better, at lowering cholesterol, but we are better at losing weight. So this is a more effective weight loss treatment than tirzepatide, which is obviously fantastic. But what was the one thing we wanted to say up front that we were super excited about? Would it be less nausea and vomit inducing than Zepbound or Ozempic, right? And the answer is absolutely yes. And if you want to look here, you can see GG3. There's that nausea marker again. You can see the purple. It's much lower than tirzepatide in green or Sema in orange. And you'll also notice we gave 200 units of GG3 compared to just 10 for tirzepatide and 10 for sema. And even at 200 units, we are markedly lower in terms of nausea than the two big guns on the market, which is Zepbound and Ozempic, right? So tirzepatide is Zepbound and sema is Ozempic. That's their chemical names. Zepbound and Ozempic are their brand names. So again, better food intake reduction, better body weight reduction. So it's even better than tirzepatide. It is just as good in terms of insulin secretion and just as good, if not better, in terms of improving your triglyceride and cholesterol levels. And we can dose much higher and not see the side effects or malaise issues that you see with the current drugs on the market. So obviously we're really excited about it. Big picture, it works by targeting 3 different receptors in your brain: the Y1 receptor, the Y2 receptor, and that GLP-1, the famous GLP-1 receptor, all simultaneously as a single drug, all designed to mimic that post-bariatric chemical hormonal change that you see post-bariatric surgery. And it seems to have actually done exactly what we would hope. There's a strong reduction of food intake and body weight without triggering nausea and emesis, which is super important to us. It has even improved chronic weight loss out to 2 months compared to Zepbound, which is the current standard of care. It can stimulate insulin secretion, which is obviously wonderful. And I didn't show you, but it also can trigger muscle glucose uptake. And that bodes very well for staving off muscle mass, because as the muscle is starved of glucose, it starts to, atrophy, and you lose the muscle mass. And so obviously, if we're showing we can continue to feed the muscle, that bodes very well for that cachexia effect I was hoping to mitigate it earlier on. It is a once-a-week injectable, which will be very useful for humans. Just want to shoot and forget about it for a week. And so we're now ready for what's called investigative new drug screening and moving into phase 1 human safety trials, which is the plan for the next 15 months or so. And so I'm hoping Syracuse University will have 1, if not 2 drugs in humans by the mid or late 2026, which I'm informed will be a first for the university. And I think it's really wonderful. And as I said, we've spun out a company called Coronation Bio. And Coronation Bio has licensed the technology from Syracuse University. Syracuse has kept a small percentage of the company. So it now owns a very young, very new, and very startup biotech pharma company that is going to develop these compounds and get them out there, hopefully helping people in the next 3 to 5 years, starting with the phase 1s next year. And so I guess with that, I hope I haven't run too long. I will thank you very much, and I'm happy to take any questions at this time.
Thanks, Rob. That's really terrific stuff. I learned a lot, and I'm sure others did too. So if you have questions for Professor Doyle, you can type them into the chat, and I will relay them to him. But Rob, you can read them yourself. Or you can raise your hand if you want to actually speak up and voice your question. There's a button at the bottom of your screen that says React. There's a little heart icon. If you click on that, you'll see a little raise hand button that you can press, and then I'll call on you to go ahead and speak. Rob, I had one question to get things started. So is there a danger that this would work too well, that someone might starve themselves or become, malnourished?
Yeah. I mean, as I said earlier on, I think our desire to eat is pretty much innate. It's very, very hard to stop eating for any considerable period of time. I think what we know is that hunger is a powerful sauce, as my father-in-law would say. Everything tastes better when you're hungry, right? Because you're driven to eat. So I guess if you have somebody who is already anorexic and is looking to harm themselves, it could be quite deadly. Absolutely. What we have found is we can stop rats from eating completely, and that's really impossible. The physiologists who I work with, they don't remember seeing anything that could completely stop a rat from eating with food in front of it, having not eaten for 2 days and still not eating it. So we really have shut it down, and we had to stop the experiment after 2 days for ethical reasons, right? We removed the drug at that really crazy high dose. We were up at 100 units, and let the animals just get back to eating again. So yes, I mean, there is the potential that but it would have to be deliberate, and it would have to be willful, and it would have to
Okay.
be at doses that shouldn't be commercially available to anybody.
Okay, that makes sense.
Yeah.
Okay, Seth has a question. You didn't speak to constipation and difficulty regarding bowel movements with the current GLP-1s. What is the experience with this new one regarding that?
Yeah, so we do a gastric motility test, and so essentially we actually use paracetamol, or we give the animals paracetamol, and we look to see if it is moving through their system and can be detected in urine at a normal standard time. And so we don't see gastric motility changes, and we shouldn't, because again we're not allowing this GLP-1 receptor to run amok and to actually tell the from the vagus communication down to the gut, shut down the muscle movement, right? Because it's that peristalsis, it's muscle movement, right? And if that stops, everything just seizes up, right? And so what we want to do is prevent that brain to gut communication that's saying, stop moving food from the stomach into the intestine. And because the food then sits there, it's very uncomfortable. And nobody's going to keep eating more if it's sitting there, right? Because you feel post-Thanksgiving dinner, all that turkey, right? You just sit down and you're like, I couldn't eat another bite. And if your stomach isn't emptying that food out into the intestine, of course, you're just not going to eat more, right? And so yeah, it is and has been a significant problem for patients who've some patients have had gastric paralysis in the most extreme cases, where it's taken a long time for them to get motility back into the gastric system, and they've ended up having to be IV'd and get food through the IV. So yeah, but so far so good in ours, right? And the proof will be in the pudding, which will be when we put it in healthy human volunteers, and every aspect of things like that would be tracked and monitored. Yeah, but all the preclinical models are standing up really well, and we are using the current standard of cares to say, look, these models are showing the same things we see in humans, but so when we test them with our drug, we're not seeing those bad side effects in humans that we see in humans. So the translation potential at least is good, but until we get it into humans, we won't know for sure.
Okay. Precious had a few different questions. I'll ask one and then we can circle back to the others once we've gotten to some other questions. One question, what mechanisms would allow your peptide to reduce fat while preserving muscle mass?
Yeah, I mean, there's various different ways that we could think about that. So without getting too lost in the weeds, unless you want me to, one of the targets that GEP44 has is this Y1 receptor. And it targets Y1 receptor, Y2 receptor, and then the GLP-1 receptor. Y1 receptor is found in muscle tissue, and it is an insulin-independent glucose uptake mechanism for muscle. It is a backup muscle accessor for glucose. And of course, fight or flight muscles hold us up, let us get away from a threat. If you need a sudden burst of excess glucose, one way to get it into the muscles is through this Y1 receptor. GEP44 has that mechanism, and that is pulling glucose into the muscle, which also, by the way, makes it a better glucoregulatory drug because it isn't insulin dependent. It has insulin efficacies, but it also can facilitate glucose uptake in a different mechanism to the normal insulin way, right? And so that is preventing the muscle from starving. And so that is, a really, really, really nice aspect of the Y1 receptor agonism in terms of protecting muscle mass loss, right?
Okay, Michael had a question. So he says, so if someone is slightly overweight and wants to lose 15 to 20 pounds, it sounds like you would not recommend one of the currently available drugs?
God, no.
Okay.
Absolutely no. Absolutely not. No.
Okay.
Unless you
Simple
try
answer.
everything else and your physician, MD, says you need to lose that 10 or 15 pounds, and if you've tried absolutely everything else, then of course follow your physician's advice. Absolutely, that's first and foremost. I'm not a physician, right? I'm much smarter than that. So I'm joking. We have to be judicious about it, and I think the FDA have come to the realization that what we have now are people who are overweight, people who are obese, and then people who are clinically obese. And what they want now is to have physicians stop giving it to people who are overweight or even obese, and to focus on giving it to people who have lots of people who are overweight or even obese are perfectly, good spirits, move around, no problem. they don't have health effects like diabetes or cardiovascular disease associated with, or NASH, liver failure, whatever. Those people need the drug the most. So they've decided to break it into two. It's now obese and clinically obese. And only people who their physicians call clinically obese should be taking these drugs.
Okay. Janine asked, is this a drug one would take for the rest of their life? So you get the weight off and you stop taking it, or you keep taking it?
No, you don't want to take any drug for the rest of your life if you can avoid it, right? There are some exceptions, of course. But ideally, what would happen is you would take the drug to get down to a really healthy, active weight. And what you find with all these drugs is they come with, apps, and they're usually tied to Weight Watchers, for example, apps, or gym memberships, or, healthy, active lifestyle communities or whatever. And the idea is that you would change your behavior as well as your appetite, right? And lose that weight. And so the idea is that when you come off the drug, you would still be out there, active. You've changed your lifestyle. If you become sedentary again and you go back to your old eating habits and you're not taking the drug, you will, of course, compensate. But the idea is the motivation that you feel from feeling active again and getting out there again. And one of the biggest things is just being able to walk a 6-minute mile. A 6-minute walk. Physicians with obese individuals, if they can get their weight down to the point where that individual can just walk for 6 consecutive minutes without having to stop, that is known to have really positive metabolic effects. And so, if you can get all that weight off and keep active and continue to be able to do that 6-minute walk, even if you do regain some of the weight, the long-term health aspects of it are without question, all positive, right?
Seth had a question that's kind of related to this. If GLP-1 evolved from toxins, what are the implications for long-term human use?
Yeah, so we repurposed. Nature likes to duplicate and repurpose and reuse. And so whereas, we evolved to use it as a glucose control mechanism and as essentially a food intake reduction mechanism, it's perfectly natural to us now. We've evolved to it, right? It's not a toxin anymore. It's been repurposed to be an endocrine regulator in humans. And so that's where it came from. So the long-term aspects of taking it, as far as we know, and all the evidence we've seen so far, they're temporary and they're associated with while you take the drug. The only long-term implication we have seen is that some patients who have taken it out to 3 years have a slightly increased risk of thyroid cancer. And so you'll see it's a black box marker that says if you have any history of thyroid issues, you shouldn't take this drug. And you certainly shouldn't take it for longer than 2 years. And I think if you have thyroid issues, most physicians would recommend you don't start taking it at all. But that's purely out of a massive abundance of caution, right? Yeah.
Tony was wondering, the current GLP-1 drugs were recently approved for chronic kidney disease, along with Jardiance and Farxiga. Do you think that the SU drug will eventually be approved for CV and CKD?
I would hope so, but baby steps. First thing is get it through humans for safety, get it into phase 2 trials for obesity. And then what you do is once you get that in hand, you do look and you do broaden the scope of benefits. It's not just kidney disease. It's shown incredible promise for cardiovascular disease. And I think you're going to see, certainly by next year, you're going to start seeing announcements that these drugs are recommended for patients with cardiovascular disease. Because patients who are obese who do take these GLP-1 drugs and have cardiovascular disease are living longer than those who aren't taking it. So, and late last year at the American Cardiovascular Society meeting where they showed this data, the physicians in the room actually standed up and started applauding, because they haven't seen that level of progression in cardiovascular improvement since early drugs discovered in the 1970s. So it's been 50 years since they've seen a bump like this in cardiovascular treatment. And so they're super excited. So it's going to be, we're only scratching the surface. These drugs are only going to get better, and they're going to be found to work kidney. They're going to be found to work in liver, fatty liver disease, for example. They're going to be cardiovascular drugs as well as weight loss drugs. And they all started off, of course, as diabetes drugs. And so what they've done is we're branching out and branching out and branching out from there. So, yeah.
Okay. We've got one more question. Precious had a question about the thyroid risk, which you answered. And then she had a question about the business side of this. I'm not sure how much this is analyzed before human clinical trials are conducted, or if this is usually done after, but with the market expanding so quickly in just 3 years, how do you plan on to break in and compete with major players in an increasingly crowded space?
Yeah, you're right. So of course we won't, is a simple answer. We'd be bought.
Okay.
Absolutely. I mean, we wouldn't have the capacity to run a phase 2 or a phase 3. Only big pharma can push things through, the late stage clinical trials like that. So normally you either partner or you're essentially bought out, and then they take your technology into their company and then they run it through, right? So and Novo Nordisk just did this last week. A company, United Healthcare in China, have a drug that's a triple agonist as well. It showed fantastic phase 1 trials. So Novo bought it from them for $200 million up front, and we'll give them $2 billion if it makes certain milestones along the way to human trials. So that's normally what happens.
Okay.
Yeah.
All right. It looks
The little
like,
fish get eaten by the big fish.
yeah. Yeah, that's great. All right. Well, I don't see any more questions, so I think we're ready to wrap it up. Professor Doyle, thanks so much for preparing this presentation and joining us this evening. It was
Yeah.
really fantastic, and I'm happy we had a chance to learn from you today. I want to thank all of our guests for joining us today. Stay tuned for more invitations to future presentations by Arts and Sciences faculty, and we hope to see you soon again. And again, we hope you can go and make a gift to SU for Giving Day. We would really appreciate your support. And if you could support the College of Arts and Sciences or the Department of Chemistry, all the better. So, Rob, thanks again.
Thank you.
Okay, take care, everybody. I'm going to ask Liz to close down the meeting now. Have a great evening.